Hello. So far we have discussed the crystal structures and how we can understand crystal structures by X-ray diffractions. Now our question is how the atoms in a crystal are bound together or what hold a crystal together. Okay. So in this chapter we are going to discuss crystal binding. So these atoms will have negative charged electrons and nuclei. So this attractive interaction between these negatively charged electrons and positively charged nuclei is responsible for binding of the atoms together or the cohesion of particles inside a crystal. Okay, so this is due to the electrostatic or Coulomb attraction between the negative and positive charged particles. Okay, so there are magnetic force, there are gravitational force between the particles, but these forces are very weak. Okay, magnetic forces have least effect on this binding. Okay, and gravitational force anyway it is very negligible. The differences between the forms of different forms of condensed matters are due to the differences in the distribution of outermost electrons and the ion cores. So there is cohesion between the particles in a solid, okay, in a crystal. So let us now define cohesive energy. So when the atoms are together or when the particles in a crystal are together, then there is cohesive energy. So what is a cohesive energy? What is defined as cohesive energy? So we know that these particles are together. Now we have to supply some energy to separate these the components of this crystal, okay, into free atoms to infinite separation. So we have to separate all the atoms to infinite separation. Okay. So how much energy is required for that? So that is called cohesive energy. So cohesive energy is defined as the energy that must be supplied to a crystal to separate its component to infinite distance as a free atom. Okay. Similarly, in some cases it is lattice energy. So in ionic crystals it is termed as lattice energy. So what is lattice energy? Lattice energy is also energy supplied to separate the components of a crystal into constituent ions, free ions at an infinite distance. So these ions are together. Now we have to supply energy to disturb the system and we have to make the individual particles to infinite distance. So now they are no longer bound. Okay. So that energy to be supplied to the system to separate its components is called lattice energy. That is in the case of ionic crystals. Okay. Now, different types of solids will have different cohesive energy. So we have inert gas crystals. In inert gas crystals, they are weakly bound. Then alkali metals crystals have intermediate values of cohesive energy, and transition elements will have very high cohesive energy. They are very strong. Okay, so their melting point, all these things also will vary accordingly. Now we will discuss the first type of crystals, that is the crystals of inert gases. Inert gases. So the inert gases form the simplest crystal. They are transparent insulators. They are insulators, they are transparent, weakly bound because their cohesive energy is very low and they have low melting temperature. Okay. So we can write one by one. They are transparent insulators. Then weakly bound. Weakly bound means low cohesive energy, low melting temperature or melting point. then the atoms have very high ionization energy. The atoms of the inert gas crystals have high ionization energy. You know why? The outermost electron shell of the atoms are completely filled. Okay. The next point is the electron distribution around the nucleus is spherically symmetric. Electrons is spherically symmetric around the nucleus. Okay. So these are the different points in the case of crystals of inert gases. Now the crystal structure of inert gas crystals is FCC. Crystal structure is closely packed structure, that is FCC. Okay. Except H helium 3 and helium 4 crystals. Okay. Now the electron distribution in the crystal cannot be significantly distorted from the electron distribution around free atoms, because the cohesive energy of an atom in the crystal is only 1% or less of the ionization energy of an atomic electron. Okay. So that means the electron distribution in the crystal is not very far from the electron distribution around free atoms. They are not distorted that much, because the cohesive energy of an atom in the crystal is about only 1% of the ionization energy of the atomic electron. Okay. But part of this small distortion, whatever may be it, this gives van der Waal interaction. Okay. So van der Waal interaction is the main interaction in the case of crystals of inert gases. So let us discuss the van der Waal interaction in the next class.